Okay, so the fundamental theorem for divergences, essentially what this does is it relates the total divergence of a vector from some point to the total flux across the surface. Okay, so it's also called Gauss's theorem or Green's theorem. And what we have here is the divergence of a vector v integrated over some volume. And d tau here is our infinitesimal volume element. And this is equal to the dot product of our vector with the infinitesimal surface area integrated over some surface. So let's do an example with this to show it in use. So we're going to test the divergence theorem for the above function. And we're going to take as our volume the cube, which is shown below, which has a length of psi 2. So first of all, let's just write out what our divergence of v is. Okay, now if you recall, it's equal to the derivative of our vx component with respect to x plus derivative of our vy component with respect to y plus derivative of our vz component with respect to z. So for the above function, what we get is y plus 2z plus 3x. So now we must integrate this over our infinitesimal volume element. So we've got the integral of our divergence of our vector d tau be equal to y plus 2z plus 3x, and for a volume element, of course, it's dx, dy, dz. Okay, so we've got a triple integral here, and for each we're going to integrate between 0 and 2. So if we first look at our integral with respect to x, okay, so for yz we go from 0 to 2, 0 to 2, and we integrate with respect to x, we will get 2y plus 4z plus, so we'll have a 3x squared over 2, and this will result in 6. Then we integrate with respect to y, so now we're left with 0 and 2. Integrate with respect to y, we get 2y squared over 2, so we'll have 4 plus 4yz, so this will be 8z plus 6y, which would be 12. And then integrate with respect to z, we will get a 8 z squared over 2, so we'll be left with a 4z squared plus 16z between 0 and 2, which would be equal to 16 plus 32, which would equal 48. Okay, so now what we must do is, what we're just after doing there is we just looked at the left hand side of this equation. Now what we're going to do is look at the right hand side. Okay, and we've got 6 sides to consider. Okay, the first side. So the first side is where x is equal to 2. So here I have x is equal to 2, and our infinitesimal displacement area, dA, is equal to dy dz x hat. So now when we do v dot dA, remember x hat dot x is equal to 1, x hat dot y hat is equal to 0. When we do v dot dA, what we get here is x, y, dy, dz, which of course is going to be equal to 2y, dy, dz. And we integrate this over for dy and dz from 0 to 2. So now the integral (0 to 2, 0 to 2) of 2y dy dz. And we do the integral with respect to y first. We're going to have a 2y squared over 2, so we get y squared. So we have 4. Integrate with respect to z, we get 4z. And this will give us 8. The second side is where x is equal to 0. So our infinitesimal displacement area is going to be, it's a negative now because it's out the other side, so we have it's in the minus x hat direction, or dy dz x hat. For v dot dA, we get the same expression as up here. So putting the x in as 0, v dot dA is equal to 0. So let's move on to a third side. The third side is where y is equal to 2. Our infinitesimal area element is going to be equal to dx dz y hat. Okay, so you can see it's just a lot of repetition here. V dot dA now is going to be equal to 2y z dx dz, which is equal to 4 z dx dz. And now we take the integral between 0 and 2. So if we integrate first of all with respect to x, we're going to get 4zx. This will give us 8z. Integrate with respect to z, so we're going to have 8z squared over 2, so we're left with 4z squared. 4 by 4 is going to give us 16. And on the other side then, we have y is equal to 0. dA is going to be equal to minus dx dz y hat. When we work out v dot dA, we're going to get the same answer as up here. So with y is equal to 0, v dot dA is going to be equal to 0. So we've got two more sides to consider, the top and the bottom. So our fifth side is going to have z is equal to 2. The A is now going to be equal to dx dy z hat, and v dot dA is going to be equal to 3zx dx dy, which of course is equal to 6x dx dy. So now if we integrate this, between 0 and 2 for the x and dy of 6x dx. We'll do it with respect to x first, so we're going to get 6x squared over 2, so we have 3x squared, which is going to give us 12, so between 0 and 2, so now we've got 12 dy. Integrate this with such y, we get 12y, so the answer we get is 24. On our final side, we see that z is equal to 0, dA equal to minus dx dy z hat. With z being equal to 0, we see that v dot dA will be equal to 0. Okay, so essentially now we've just completed everything. And what we must do now is we sum up this. So we get 0 plus 24, 24 plus 16 gives us 40. With that 0, we're still at 40. Plus 0 is 40. Plus 8 is 48. Okay, so what we find is that we get the same answer as we did previously, and that our divergence theorem holds.